So here, this was kind of the kernel that we used last time, and let me. Okay, so this is what we had last time. What if instead of these kernels, we increased the what we're going to call the bandwidth of each of these Gaussian curves? Okay. So when we increase the bandwidth of each Gaussian curve, what it looks like. So here, you know, I've got -1, 0, and 1 again. Got data points here, 2 right there, and 1 right there. Instead of having these kind of these sharp points, what if I have these kind of these lazy curves that have a great amount of width? Something like that for the two curves centered there, and then something right there. And so when we add them together, what do you think this overall curve would look like? Okay, so if we add all of these together, it's going to generally have a much more, just a much smoother appearance. Something like that, okay? When you add them all together, maybe something like that. And so this is changing the bandwidth to a wider bandwidth. Okay, so over here we have use a wider bandwidth. Okay, and then we add those curves together, and we get, you know, a much more kind of smooth distribution here. Okay, and so there's a lot of discussion. Okay, you can go to Wikipedia and look up kernel density estimation. Okay, kernel density estimation, and talking about kernels in general, there's a lot of discussion about the appropriate bandwidth that you should be using. Okay, they have the rule of thumb bandwidth estimator, the you know, these different bandwidth functions, and exactly how the resulting thing would look. Okay, we also have a selection of kernels. Here I've been using Gaussian kernels. Okay, but we could also have different shaped kernels as well. So let me create a new chart here, or new. So we'll have different kernels. So here we can have either what we call a uniform or rectangular kernel. So here, let's just say that I have 2 dots right here. Okay, so for the rectangular kernel, instead of adding kind of this nice Gaussian curve, it's going to look like this. Here I've got a rectangle here, and here I'm going to put another rectangle over here. And then so when I add these two together, what will our resulting plot look like? It's going to be a rectangle, but right here, because these two are being added together, you're going to kind of get this funny little action here. Okay, this is what using a rectangular kernel would do. Okay, and so with a rectangular kernel, you get something a lot more jagged. We also have, you know, triangular kernels. Okay. And so with a triangular kernel, let's just, oops. So let's say I have 2 triangles right there. What the triangular kernel looks like, you've got a triangle centered right here and a triangle centered right there. So what is this thing going to look like? end up getting something that goes up and then maybe down a little bit, and then where these two things add up together, they kind of form this flat thing, and then you add up and you get something that looks like that. Okay? And these are just silly examples just to illustrate what's going on because we're only using 2 points. Okay? Of course, if your sample is only size 2, you would not perform kernel density estimation, and nobody in their right mind would use a sample of size 2 to try to figure out the shape of the population. Okay? But effectively, this is what we're doing. We're just collecting a whole bunch of data, okay, and a histogram where we're just adding blocks together. Instead of using that method to get the general shape, we're taking kernels, which are either these smooth functions that look like Gaussian curves, or maybe something that's a little bit more angular, like the rectangular or the triangular kernels. Okay, and you can look up kernel on Wikipedia, and here's kind of a chart showing you the different kernels that we have. We've got the uniform or rectangular, the triangular. Okay, this is the eponechnikov. Okay. Basically, it's just an upside down parabola. Okay, it's just a parabola upside down. Huh? Say that. Eponichno. Russian, yes. I'm sure it is not from the U.S. Maybe, but yeah, it's an upside down parabola. Okay, I wish they just called it upside down parabola. That would make it a lot easier. But but this is what it is. All right, and then you got all of these other things, the tricube and the, but probably the one we're most commonly used is the Gaussian, just because it's smooth, and so you got these. It levels off nicely as it goes to the edges, and it adds up nicely. Okay, but you have all of these other things, and here's kind of what they look like, all on the same thing. All right, so let me just kind of show you what this looks like practically in R, and we'll just fiddle around with this. And again, this is just a very high level showing you how kernel density estimation works. The mathematics and the calculations behind it are a bit more complex, but I think if you just understand how these things are working, that's good. Okay, so let's just we'll just start off with the most simple sample, and we'll say -1 to 1. Okay, or not -1 to 1. Just we have 2 points in our sample, -1 and 1. All right, and so let's do. You can do density of the sample, and what it spits out is this thing. All right, and it's saying you got 2 observations, and it's going to give you kind of this bandwidth and do this. Now, this might be helpful, but the plot is really what we're after, okay? Because when we're talking about the shape of a distribution, I think what we're really thinking, we have this visual picture of what that distribution looks like, okay? And this kind of makes sense. We have a spot at -1, a spot at 1. We're adding 2 Gaussian curves together, kind of like that. They add together and they form kind of this peak here, right? I could change the bandwidth for our density estimation, okay? And again, there's kind of a default method for determining the bandwidth, and we can see the bandwidth that this has used is 0.5847. Let me show you what happens if I increase the bandwidth to something like 1, okay? We're getting a wider thing, and now our data points of -1 and 1 give less information about the spread of our distribution, because I'm specifying the bandwidth here, and instead give more information just about the location of its center. Okay, and I can increase this, and we can see that as I increase our bandwidth, it just, at this point, I'm basically telling the thing that it has a kind of like a standard deviation of 10 by saying bandwidth is 10, and so we're getting basically a normal curve. And effectively what I'm saying is, oh, we've observed 2 very small, or 2 observations right here at -1 and 1, so our center is going to be right around 0. But as far as the standard deviation goes, I'm kind of specifying it and saying I'm thinking the standard deviation is around 10. And so we're getting this wide shape. On the other hand, I can decrease the bandwidth. Okay, and we just the bimodal nature of our data, because there's only 2 data points, becomes more pronounced. Okay, again, we would never actually do density estimation using a sample of size 2. That would be just a bad idea. Okay, let me just show you what would happen if we changed our kernel that we used. Okay, so we can change the kernel. Instead of the standard Gaussian, we can say we want rectangular. Okay, and this is, we kind of get the picture that we saw right here. Okay, we're adding basically 2 rectangles together, and this is what it looks like. If I change the bandwidth here bandwidth is 0.58. If I decrease it to 0.5, I have 2 rectangles. If I increase it to 1, we get something that looks like this. Okay, so this is what happens when we have a rectangular kernel. We can change it to a triangular one. Okay, and it looks, I think this is kind of what the picture I drew here. Again, you can imagine 2 triangles being added, one centered at 1 and the other at -1, and those 2 going together. And again, if I decrease the bandwidth, it becomes more pronounced, the bimodal nature, and if I increase it, you get something that looks different. Okay, and so at this point right here, the other triangle is overlapping the other triangle to a point where you get almost like a little steep edge right there. Okay, let me show you the upside down Epan Chech. I'm sorry. All right. Okay, and this is, you got 2 upside down parabolas kind of adding together, and you get this funny little nub in the middle. If we can change the bandwidth to something less or more. Okay, and all of this. So that's all to just kind of show how this works. Let me change my sample to -1, 0, 0, and 1, and we'll do kind of some of these similar things here. Plot density of our sample 2. This is our default thing. Okay, we get that shape there, and if I increase the bandwidth to something greater, it really smooths out the shape there. Okay, the default bandwidth here is 0.245. Even just a small increase to 0.4 or something kind of smooths things out a lot. Again, we can do rectangular. Whoops, I have to say kernel is and that's what it looks there, and then we'd probably want to increase our bandwidth. Whoops, maybe not 3, but something. And you get these kind of these strange shapes going on when you adjust these. Okay. Anyway, so these were all just kind of toy examples showing how the kernel density estimation works as far as just adding curves on top of each other. We would use this in a case where we have some data here. Okay, so let me set my working directory, and we'll use our okay, and so I'll load up the Latino Education Achievement data set that we've been taking a look at. And so in that one we have we do read.csv, and it's called latinoed.csv, I believe. Okay, so that's loaded up there. And so our value and achievements achievement levels are stored right there, okay? And so a lot of times we would get an idea of the shape of our data by just doing histogram Latino $ achieve, okay? And this is a perfectly valid, and I still think using histograms is very useful. And we can change the kind of the bin width of our histogram by increasing or decreasing the number of breaks that we have. So here I bumped up breaks to 20, and we get an idea. Just they're very similar, but they show by increasing our breaks we get a little bit more detail into some of this. Okay, and so what we might want to do instead of doing a histogram is that we can do density. All right, and we would plot this, and this is all using just base graphics. ggplot also implements plotting density curves. Okay, but I forget what the exact command is. I think geom density is pretty much what you're going for. Okay, and you plot this, and comparing this versus this is you can see a lot of similarity in terms of what the histogram looks like, especially what this histogram versus this density curve looks like. Okay, and this just uses kind of the default Gaussian curves for the density. But we can see what would happen if I adjusted the bandwidth. Right here my bandwidth is 4.2. If I decrease the bandwidth to like 3, we see, or 2, we can see the thing get more and more jagged as the data, as we decrease the bandwidth. Okay, and on the other hand, I can increase the bandwidth, and it just gets more and more smooth. Okay, it looks more and more like the normal distribution. So this is just kind of adjusting the bandwidth. The default level is R calculates using some equations there. Okay, and we can also show you what happens if we change our kernel from the standard Gaussian to rectangular. And so because the rectangular has the sharp edges as far as the kernel goes, the resulting density estimation will also have these sharp little edges. Okay, so because this thing has sharp edges, so when two things kind of add up or don't add up, you get these very sharp edges as well. Okay, similar to the triangular, you're going to get some. It's a little harder to see, but you do have a little bit of jaggedness in certain locations as well. Okay. But the density is a useful way, and much in the ways that the histogram is useful for revealing shapes, so is kernel density estimation. And so we might want to do a plot where we're comparing the density of those who came from Mexico versus those who did not come from Mexico. All right, and so here I would create so we'll just kind of default to this, and so this will be our original density curve, and to this I can add a line where I'm going to plot density of Latino $ achievement, but I'm going to subset it where Latino $ Mexico is equal to 1, and we're going to, because we're going to change the color here to red. Okay, and so this is the curve, density curve for those coming from Mexico, and then we'll also add a line for those not coming from Mexico, and we'll do that one in blue. Okay, and so here we see one of the problems with base graphics is that it defines the kind of the plot settings based on the first graph that was created, and so here it needs to adjust the y limits of the thing, but here we get an idea of how these density curves compare to each other. Okay, and anyway, so just like histograms density estimation is susceptible to some jaggedness, especially when the samples are small. Okay, when the samples are large, density estimation works really great, and it looks quite nice as far as the distribution will go. But when the samples are small, you're going to get a little bit more more jaggedness. And so there's kind of this question: is there really a peak here and a dip here in the thing, or is that just an artifact of having a small, fairly small data set? Okay. Looking at the overall density plot, though, it does appear that there is a little bit of a left-skewed nature in terms of the education achievement levels as far as immigrants from Latin America go. So there does seem to be some left skew in the data, and but there's one thing to watch out for is that if I look at the summary of our data, what do you think the minimum value is in our data set? Kind of looking at our density plot. Okay, let's see. So the minimum value is 21.5. Okay, so that's something kind of around here. And so all of this the edge of the tail, okay, and our maximum value is 96.2. So that's actually kind of probably around here. The edge of the tails are almost always just an artifact of the kernel that we're using, okay? And so that's just something you got to watch out for. I mean, just because with kernel density estimation, we kind of like to have these things smooth out towards the ends. It just continues off here. So don't look at this and say, oh, we've got data down here at 19 or something. Almost certainly, it's always just a little bit pulled away from the edge of the data there. Okay, so you can kind of count. So here our bandwidth is around 4.3, and it looks like the edge of this thing is around 17 or something. You can kind of expect the smallest data point to be kind of where this thing gets the smallest, and you add, or where it gets biggest, and you subtract some of the bandwidth there. Okay. All right. So this is kernel density estimation. You don't have to worry about this being on the final exam, but I thought it would be at least to your benefit to show how these functions work, because I think in the future, as far as your data analysis goes, this is a very useful function. I put it just as useful as plotting histograms go. So you probably make lots of histograms. Another option is to use the density function to kind of get a slightly smoothed out picture of how your data might be distributed. Okay, we'll end there. We'll see you guys on Friday. Please take a look at homework 6, which has been posted, and give it a good faith attempt on it. Okay.